it again. Minus 25 power 3 times by 2 power 3 divided by 3 plus by 2 power 3 times by 0.2 is equal to 333. Yeah, 33. No, something is missing. Oh no, it's correct. Okay. So that is our at C. We have X. We have our shear force and bending moment diagram. Points. Okay. Next, we look at between. Okay, I leave for you guys to copy first. Okay. I see. Is there any question? No one is asking. Anyone have questions so far? I don't hear nothing, so you all can remember this. Now, next I'm going to copy the diagram again. Okay. So now we are going to form between point C to point D. Okay, between point C to point D. Okay. So i.e. 0.2 x and 0.4 meters. That's the limit now. Okay. So now be careful when you construct your shear force diagram now. Okay, why I say be careful? Oh, sorry, your bending your bleh, your diagram. Okay. So this is point A, right? This is where your point C is. So we know that this is equal to 2 times 10 to the power 3, right? So the distance from here to here is x. Okay, there is x. We are also aware that the distance from here to here is 0.2. So between A and C, you have an equivalent load, okay? And the equivalent load now will be a constant, okay? It will be a constant. Because x, because the equation we form is between 0.2 to 0.4. So between A to C, we pass that point already. So this will be a constant. So this load will be half times by base times by height. So that equivalent load will be 0.5 or half times by 0.2 times by 10 power 3 is equal to 1,000. Okay. And then we know the distance from here to here. Right? We are aware that this distance will be equal to what? This distance will be equal to 2/3 multiplied by 0.2. Let me write it somewhere further. So we are aware that this is 2/3 multiplied by 0.2. Right? So this distance will be equal to 2/3. That's by 2. So this is 0.1333. Okay. So we are also aware that the distance from here to here is x minus by 0.1333. Okay, we know that. Now, at point E, I'm going to change color now. Okay. From C onwards, you have a evenly distributed load. And the distance from here to here, right, is x minus by 0.2. Okay. This equivalent load over here, right, this equivalent load over here is equal to what? It's equal to 10 times 10 to the power 3, right, multiplied by x minus by 0.2. Oh, it is getting ugly and messy now. And the distance from here to here is equal to x minus 0.2 divided by 2. Okay. Then we are again going to make the assumption of positive shear, positive bending moment. Why is it in that direction? Because we are still our analysis direction is still going from left to what? To right. Okay. So positive. So now we do static analysis. Okay. Now regarding shear force and bending moment equation, the most important thing to sort out is see what I've just done. I figure out the forces, and more important is the distances. Okay, distances is always at the dot. Okay, you have to know that distance from that dot to anywhere on the what? On the diagram, on the free body diagram. Okay, so sort out the distance, then you will not make so much mistake. If you have no distance, later on when you do your moment, you will be as lost as anything else. Okay, okay. Now let's go. Static analysis. Dimension about forces in the y direction will be equal to 0, right? So this will be equal to 2 times 10 to the power 3. Okay, minus. Okay, so down here we see that it's minus by 1,000. Okay, minus by 1,000. Right. Then the next one is minus by 10 times 10 to the power 3. Right. X minus 0.2. Okay, so that is our force. Okay, and then the last one. The last one is minus b as a function of x is equal to 0. Okay, so this will be equal to 1,000 minus by 10 times 10 to the power 3. X minus 0.2. Okay, so this whole thing is v as a function of x. Okay, so now when we write things out, v as a function of x is equal to minus 10 times 10 to the power 3 x. Okay, and then plus, no, this is minus will be plus. Wait, yep, will be plus. Hold on, 0. Yep, it's correct. Will be equal to 0.2 times 10 to the power 3 is equal to 2,000. Okay, and then plus by 1,000. So this is equal to minus 10 times 10 to the power 3 x plus by 3,000. Okay, now this is our equation number 3. Now, how do we know that this equation is right or wrong? Okay, so we can check. Okay, we can check. So the way we check is when x is equal to 0.2, okay, v as a function at 0.2 should be equal to 1,000. Why that's the case? Because this is v at point C. Okay, we can check at point C. Because v at point C, the magnitude at equation number 3 and the value or the equation number 1, you should get the same value. Okay, so we just plug in now. So we check. So this is equal to minus 10 times 10 to the power 3 multiplied by 0.2, right, plus by 3,000 is equal to, so minus 10 power 3 times 0.2 plus by 3,000 is also equal to 1,000. Okay, so this equation is good. Okay, then now we are going to form the moment diagram, moment equation. Okay, so we're going to do the moment equation. Question for you: when you were learning this in 2P, do you form the shear force and bending moment equation? Yes or no?
Yeah.
You did this, right? Okay, good. Okay, so just to recall, now there are two ways of doing this. Okay, this is using static analysis. You can also use the integration method. Is the same. Okay, can you zoom out, Julia? Can I zoom out for a second? Sorry, Julia. Are you seeing what you are seeing, or am I missing something, Julia? Are you okay? Go on. I'm waiting for Julia to see she fine. Julia Kaminsky, you okay? Okay. Okay, I think Julia is okay. Okay, so the next thing is we're going to take moment. Now, aren't you glad that you have all the distances sorted out? Okay, with all the distances sorted out, it's easier to get your bleh, tongue twister I'm having, to get your shear force equation. Okay. Now, if we look at our shear force equation, right, is a linear equation and it has a negative slope. Okay. So now we are going to do summation of moment in the z-axis at point x. Okay. So this is where we are going to take our moment from, the dot which I highlight. So the first one is the 2000 is going to be clockwise, so minus 2 times 10 to the power 3 x, right? Okay, minus and then the next one is plus by 1000, and we know the distance x minus 0.1333. Right, we got that. And then we have again plus, okay, 10 times 10 to the power 3 x minus 0.2. Okay, square the whole thing divided by 2, right, because of the distance, right? And then you plus by m as a function of x, and this is equal to 0. Okay, so when we tidy it, I'm not going to make it to a simpler form. Okay, I'm going to write the equation, then I'm going to sketch the shear force and bending moment diagram. So m as a function of x is equal to minus 5 times 10 to the power 3, right? X squared minus by 2 times 0.2, 0.4.
Eugene.
Yes.
How come that's plus mx? I thought it was supposed to be minus mx.
Anti-clockwise.
But did we not do minus mx for like between A and C, or did I just write that down wrong?
Between A and C. It's also plus.
Oh, I just wrote it down wrong. My bad.
Okay, because we are doing positive shear and positive moment assumption. Okay, and we are doing from left to right. If you do from right to left, then you're right. Then it's minus. Okay. So coming back to here again. Okay, so 2 times by 0.2, 0.4. So 0.2 times by 0.2 plus by 0.04. Okay, 0.2 times by 0.2, 0.04. Then you have minus 1000 x minus 0.1333, and then this will be plus 2 times 10 to the power 3x. I say I'm not going to solve it by myself. Okay, let's do it all the way. So this will be equal to minus 5 times 10 to the power 3 x squared plus by 5 power 3 times 0.4 is equal to 2000 x minus by 0.04 times by 5 power 3 is equal 0.04 times 5 power 3 is equal to 200 minus by 1000 x plus by 1000 times by 13.1333, 13.133.3 plus by 2 times 10 to the power 3x. Okay, so this is equal to